Minutes completely, or are you?
So I time myself.
It's my pleasure to introduce Ophir Nakum today. He's from Google Brain and originally studied at MIT, then did a few years at Quora, worked as an engineer for their machine learning pipeline, and then went on to Google Brain and has now been doing research on RL for 3 years, right? Mm-hmm. Working mostly on hierarchical RL and the connection between policy-based and value-based RL. Mm-hmm. Yeah, and we'll see a very exciting lecture today.
Yeah, hopefully.
Yeah.
So thanks, I'm glad to be here. Yeah, so today I'll talk about some much more recent work, of me looking into applications of contextuality in RL. So before we get into like the meat of the lecture, let me try to give some motivation about why contextuality and why should we care about it in RL. So the summary is that in RL, those several sticky situations that often come up, mostly having to do with the fact that when you have an environment, you only have access to samples from it, and not necessarily like explicit knowledge of what the environment is. And it turns out many of these can be solved by an application of duality. So let me show you a few of these sticky situations. So first one is minimizing the squared Bellman residual. So this is pretty common, like you want to do value learning for a policy pi to estimate its Q values. So what you want to do is just minimize the expected Bellman error given here, right? So if you have some Q function, minimize the difference between Q and the Bellman backup of Q, which is the expected reward plus expected next Q value. But the issue here is that you can't actually compute this expectation because in reinforcement learning, you don't have access to T, you only have access to transitions. So you really only have access to a single next state for each state and action you have. Right, so in general, we just have transitions, but what people usually do is the following. They say, well, I'm just going to sample transitions and then minimize the sampled square Bellman error. And most people do this, and in most cases, it's fine, but it's actually wrong. And the key issue is here, where what we want to do is on the left-hand side, right? Minimize the squared Bellman residual, but what we're actually doing is minimizing squares of sampled Bellman residuals. The key issue here is that there's an expectation inside that Bellman operator on the left-hand side, and that expectation is inside the square. And what people usually do is just say, well, I'm going to take that expectation outside the square and hope everything works out. But in general, these aren't equal, and this is a problem. It's usually referred to as bias gradients or double sampling issue. And what's the fix? Well, we'll look at how convex duality can actually provide a tractable training objective for this without actually doing the wrong thing. So that's one application. Here's another so-called sticky situation where you want to regularize a policy to some behavioral data. Right? So you have, you're learning some policy, you want to maximize rewards, but at the same time, you maybe want to minimize or constrain its divergence from some behavioral data. But you actually don't know the policy that generated that data. And so this is akin to like, you want to do TLPO. Like TLPO is saying, I want to learn a max reward policy, but that's constrained via some KL divergence from my last policy. But in this case, you don't know your old policy. All you have is access to samples of interactions from that old policy. And this comes up a lot in practice, like if you have like, if your data is coming from humans, then you obviously don't know what policy the humans followed, but you still potentially want to constrain your policy to not go too far from what your human data is showing you. Okay, so we want to estimate, for example, in like the TRPO case, this KL between our current policy and the old policy being pi 0, but we don't know what pi 0 is. We only have access to samples from it. So how do we do this? Well, with an application of convex duality. So here's a third application, off-policy policy evaluation. So again, the theme is you don't have explicit access to your environment. You only have access to samples from your environment. And in this case, you want to estimate the value of a policy. Okay? So you're given some finite experience data set. You don't know where it came from, right? Like it might have come from a human demonstration or might have come from a bunch of old policies you don't have anymore. And now you want to estimate the value of this policy, meaning if I were to run my policy in the environment, what would the average per step reward of that policy be? And this comes up in a lot of applications, like when you have a policy that you're training for like a health application or even like YouTube recommendations. It's very expensive and sometimes dangerous to actually run a policy in the environment. But you still want to have some way of understanding, given a policy, is this policy good or not? Is it actually worth trying to put it into the environment? So in this application, the answer again is some application of convex duality. And here's the maybe more interesting version of that. So now you have access to some experience data set. You don't know where it came from. And instead of wanting to estimate the value of some policy, you actually want to find the optimal policy. You actually want to do policy optimization on this experience data set. So specifically, we want to perform something like policy gradient, right? Where we know the gradient of the policy is going to be this expression, where it's the grad log pi times q values, taking expectation over the on-policy distribution. But then the issue is we don't have access to the on-policy distribution. We only have access to this off-policy distribution given by dd. And what people usually do is just ignore the problem. So like there's a lot of actor critic algorithms, or so-called off-policy policy gradient algorithms that say, well, I'm going to do policy gradient, but I'm just going to change the expectation. And sometimes it works, but in general, it's the wrong thing to do. So the question is, how do we get the real policy gradient we want to do without actually having access to the on-policy expectation? And what I'll show is that this, again, can be approached using convex duality. OK, so hopefully that provided some motivation. There's a bunch of sticky situations encountered in RL, minimizing the square Bellman residuals, regularizing a policy to some behavior data, which you don't know where it came from, doing off-policy policy evaluation, and even doing off-policy RL. And all these can be approached using ideas from convex duality. And that's what I'll talk about in this talk. So I'll begin with an overview of convex conjugates. And it's important for me to note that this overview will be very brief, and it'll be very informal. So right, I'm only going to give you the bare minimum that you need for these applications. And to be honest, most applications. But if you want all sorts of resources, it's going into convex analysis and in as detail as you want it to be. And then I'll go over those applications, like how do we actually apply these ideas to the sticky situations I introduced. OK, so let's get started with this very brief introduction to convex conjugates. So here's the definition of a convex conjugate. So for some function f, we define the convex conjugate as another function, f star, and that function is a result of an optimization. right? We take an optimization, max x of u times x minus f of x. And so you can think of, if you want some geometric intuition, you can think of, here's a graph of y equals f of x. It's some convex function. And then what this optimization is doing is saying, well, I have some line with slope u. And it's asking me, how far down should I move this line with slope u to get a line that's tangent to my convex function f? And how far you move it down is the conjugate function. So the conjugate function maps a slope u to how far you need to move that line down to get a tangent to your original function f. So at first glance, it's kind of weird, but it does have a lot of very useful properties. Before I get into those properties, let me show you a few simple examples. So let's say this is our original function, f of x equals half x squared. What's the conjugate? So what we need to do is solve this optimization. And we can see that, well, to find what the optimal x in this optimization is, we can just take the gradient and find, OK, the optimal x should satisfy this. U minus x star equals 0. So x star is u. And so we can plug x star equals u back into that expression and find that the conjugate function of u is u times u minus a half u squared, which is just a half u squared. So we get this nice result that if you have a square function, then its conjugate is actually itself. Here's another simple example. So f of x is the exponent function. Again, the exponent is convex. And what we want to know is, what's the conjugate? So again, we have this optimization that we need to solve for some u. What is the optimal x that optimizes this? And then what's the optimal value? So first, what's the optimal x? Well, we take the same approach. We say, well, the gradient has to be 0 at the optimal x. So x star satisfies this equation. U minus exponent of x star is 0, which means that x star is just log of u. And so we plug that x star back into the expression and get the conjugate of u is u times log u minus exponent of log of u, which is u log u minus u. So those are some simple examples. And here's the basic, perhaps like the climax of most convex analysis. It's this nice convex duality. So we introduced f star as sort of this weird definition, but the definition is the right way to get this nice duality where you have, for any convex function f, the conjugate of the conjugate is the function itself. So what this means is, not only can you write the conjugate as an optimization over the function, but you can write the function as an optimization over its conjugate. And this will be very useful in pretty much all the applications. And then the second nice property is that the derivatives of convex conjugates are inverses of each other, meaning like if you look at the derivative of f, look at the derivative of the conjugate, apply them in either order, and you'll get the identity function. You can derive this pretty easily by saying, well, let me call like u star x this argmax of u of this optimization, and this optimization is back is giving me f of x back, and we know u star the derivative of f at x is going to be just the optimization, because if you take the gradient inside here, it's just linear in terms of x, so you get back u. And then you can ask, well, what is u star of x? Well, it's the optimum of this expression, and the optimum of this expression should have a 0 gradient, which means that if you take the derivative of the conjugate function at this optimum, it'll give you back x. But anyways, I guess if you don't remember anything at all about convex conjugates, this is all you need to know. One, that the conjugate can be expressed as an optimization over its function, and conversely, a function can be expressed as an optimization over its conjugate. And two, that the derivatives of a function and its conjugate are inverses of each other. So at least remember that, if not for the rest of your life, for the rest of this lecture. OK, so that's all you need to know. And now we can get into actually applying these ideas. OK, so the first application is this idea of minimizing square Bellman residuals. So if you remember, we have this. Let me turn down. We have this learning objective we want to solve, where we want to minimize square Bellman residuals. And the issue is that there's an expectation. The Bellman operator is inside the square, which is an expectation. Is there a way to turn down the volume? This? No? Maybe.
That's the microphone. I can ask.
Oh, maybe the laptop.
Oh, yeah.
OK. OK, right? So the issue is that there's an expectation inside the square that we can't explicitly compute. And so how do we optimize this objective? So what we can think back to is the f of x equals half x squared function we had. And we know that we can express this function as an optimization, and a pretty simple optimization. And so we can do the following. We can write half Bellman squared as an optimization itself. Right? So half of the Bellman residual squared is an optimization over u of the Bellman residual times u minus half u squared. And this is pretty amazing, because now we've actually taken the expectation from inside the square, and now it's outside the square. And now it's only involved in a linear term, which is very good for expectations, right? Expectations and linear terms interact very well. And so the same way we can write a single Bellman residual squared as this optimization of a linear minus a convex regularizer on u, we can write that objective we care about as itself an optimization over some function u. Right, so on the left-hand side, we have the expectation we care about. That's the expectation of squared Bellman residuals. And we can write each of those squares as an optimization over some u, scalar u. So we can expand that to just not a scalar u, but a function that takes states and actions and maps them to scalars and get the following. So now we have, we've written the average square Bellman residual as a max over functions u of expected Bellman residual times u minus a half u squared. And you can write this in terms of transitions too, right? Because now the Bellman operator, which is an expectation, is just interacting with a linear term. So we can take that expectation of next states and next actions outside. And again, the important thing we've been able to do is take this expectation from inside the square to outside the square. And now the square is actually on the dual variable we introduced, the u. OK, so in terms of a finite sample, this is what you have. Before, I was minimizing q to optimize these square Bellman residuals. Now, I'm minimizing q, but then I have an inner optimization over u of a single sample Bellman residual times u minus a half u squared. And we can compare this to the typical biased approach, which says, OK, I'll take a single sample from the Bellman residual, but then I'll just square that and call that my objective. And so we can see that, OK, now we're doing the right thing, but there's a trade-off introduced, right? We've traded off bias, so we're doing the right thing, but now we've introduced this extra optimization over u. So is this better or worse than what we had before? Well, it depends on your context. So it's up to you and your application to decide whether this trade-off is worth it. And in some cases, it is important to have the right objective, even if it means doing some extra work with this extra optimization over U. And then this trick is sometimes called dual embedding in the literature. But it's just, as you can see, it's a pretty simple application of the convex duality properties. OK, so we did one application down. Now to the second application of regularizing a policy to some behavior data. So again, in this case, we'll in the application of we have some policy, we're optimizing, we want to maybe do TRPO with it. So we want to constrain the policy to not move too far from our behavior data in terms of a KL divergence. But we don't know the old policy that generated this behavioral data. Right, so all we have is the data set. We don't know what policy generated it. But what we want to know is how do we estimate this average KL divergence? And if you recall in TRPO, when you know pi0 and you know it and it has to be Gaussian, then you can actually compute this in closed form. But in this case, we don't know pi0. It might not even be Gaussian. It might be like a human doing something. But we still want to be able to estimate this. So the first observation you can make is that is looking at a slightly more general problem. So you can write the KL divergence as a more general F divergence. And this will allow us to more easily apply these ideas of convex duality. So for an F divergence, you just need a convex F, right? So those are all the conditions we need to apply the tricks of convex duality. So given a convex F, you define the F divergence like this. Of if you have some distribution P, you have some distribution Q, the divergence is the expectation of the F applied to the density ratio with expectation taken over Q. And then the KL is just using f of x equals x log x. So if you take x log x as f, now you have an expectation over Q of the density ratio times log density ratio. And then you have this nice simplification that happens because the Q in the expectation cancels with the Q in the denominator of the density ratio, and you're just left with an expectation over P. And now this is exactly the KL, right? The expectation over P of the log density ratio. So that's the KL divergence as an F divergence. Before I move on, I will note that this little trick, I don't know if you've seen it before, but it comes up a lot, and it's important to keep in mind. It will show up later in this talk as well. The general importance weighting trick says that if I have any function and I multiply it by a density ratio and take expectation over the distribution showing up in the denominator of that density ratio, then the density ratio reduces, and you just get an expectation over the numerator in the density ratio. OK, but back to the KL divergence. So the KL divergence is an F divergence. And we know for any convex F, we can write it as its conjugate. So we can do this in general, writing an F divergence as in terms of its conjugate. Right? So we've taken F and instead written it as an optimization over some x of the density ratio times x minus the conjugate of F applied to x. And then like we did for the Bellman residuals, we've got a max over scalars inside the expectation. But we can just interpret that as a max over functions of actions mapped to scalars. Right, so now we have an optimization over some function, and then inside the optimization, an expectation of density ratios times that function minus the conjugate applied to that x. And now we can split this expectation into two. So now we have, in the first expectation, the density ratio times x in the second expectation, just the conjugate. And then we have this nice importance weighting trick where, OK, again, we have a density ratio, and the denominator Q cancels out with the expectation Q, and we're left with just an expectation over P. So this is a very useful form of depth divergence. Maybe lots of people have seen it before, not sure. But it's a nice way to take your F divergence and instead write it as some optimization. And optimization is very nice because now the optimization, you're optimizing over X, and all you need is access to samples from your two distributions. Whereas before, you would need explicit knowledge of the densities of those distributions. So why does this matter for us? Hopefully, you can see that this is very useful, right? Because now, in our application of regularizing a policy to some behavioral data, we also have this issue where we don't know our behavioral density explicitly. We only have access to samples from it. And so what can we do? We can write the KL divergence, which we want to estimate between some unknown distributions, and write it in terms of this optimization. We're optimizing over X, and all we need is access to samples from our two distributions. And so in terms of our original problem, we want to estimate the KL divergence between two policies, but we don't know one of them. We don't know pi 0. Well, we can write the KL as an optimization. All right, so now we have expectation over states, optimization over functions X, and then inside the max, the optimization over X, we just have two expectations. So we need samples from our pi 0 and samples from our new policy pi. And then like we've done a lot of times before, we can take the max inside, which is over functions A to scalars, and just take it outside. So now the function is over states and actions mapped to scalars. And the expectations become, all we need is sample states from our distribution D, sample actions from our pi 0, sample other actions from our pi, and then inside the expectation is that difference. And then we're almost done. The last thing we need to notice is just that, well, when we sample states from D and actions from our behavioral policy pi 0, that's just sampling state action pairs from D. And so now we have this nice way to estimate the KL divergence. It's just all we need to do is perform this optimization over X, which involves only having access to samples of state action pairs from our data distribution and actions from our new policy. OK, so in summary, we've derived this optimization as an estimate of the KL divergence without knowing pi 0 at all. So again, this is pretty cool. Like now you can, if you want, you can do TLPO on a non-Gaussian policy or on a policy that you don't even know. Or maybe you don't want to regularize the KL divergence. You want to regularize with some other divergence. But again, we can ask the question, well, is it better or worse than what we had before? It depends on the context. Because now, well, we don't need to know pi 0, but we do need to perform this optimization over X. So yeah, it depends on the context, right? Like if you are doing TLPO and you know what your policy is, and it is Gaussian, I wouldn't ask you to do this optimization. I would just say compute the closed form exactly. But if at least one of those properties is missing, then maybe it does make sense to perform this optimization to estimate the divergence. OK, maybe, let's see. Let me take a maybe 2-minute break before we move on to the next section. Any questions, meanwhile? Should I?
For the optimization problem, how would you solve for X? Since you're optimizing over a function, would you solve
you would, yeah, X would have to be like a linear function or neural network, and you just do gradient descent on this objective. We do have this box. Should we try it? Do you have a question?
Yeah. Does this work? Yeah. So you moved the maximization over x outside of the expectation, but because of that, you paid the price that x now needs to map from all states and all actions to real values when it was inside the expectation. Because your data set's finite, you only need to care about the states that actually appear in your data set. Is that the case?
Well, even when you take the max outside, you could say like, well, I only care about the values of x that come up in the expectation. So I think either way, you have to care about the same number of values.
I see. So you don't pay any price by moving it outside.
All right, I guess we can continue. Thanks. Okay, so maybe the last two applications were pretty simple. Maybe the next two will be more interesting, like we'll actually start doing RL. So the first one is off-policy policy evaluation. So before we can think about actual RL, the perhaps simple problem we can approach first is off-policy policy evaluation. So you have some policy, and you also want to estimate the value of its policy. The value is the following. So I've taken, if you were to run your policy in the environment, it would get some sum of discounted rewards. And here, what I've applied is gamma discounting, or gamma averaging. So I'm multiplying by 1 minus gamma outside, and that just says what's the average per step reward of my policy, using averaging over steps given by gamma. So if I actually had access to my policy and can run a bunch of Monte Carlo rollouts, then this is very easy. I just average those. But in general, you might not have that access. In general, you only have access to an offline distribution. So usually it's expressed as a set of transitions, the D, the S, A, R, S prime. To make the notation easier, I'm going to assume this sort of access to there's some distribution over state action pairs, which I don't know explicitly, but I can sample from. And then given a state action, I can sample a next state. But only one next state, so I can't repeatedly sample from T. Okay, so we have this very loose access to the environment. We only have some arbitrary state action distribution. We don't know it explicitly. We only have access to samples from it. And we want to estimate the value of our policy. So the first step we can do is reduce this off-policy evaluation problem to a density ratio estimation problem. And the key is, so before I wrote the value of the policy as in terms of like, OK, first run it in the environment, sum up the rewards, and then average those rewards over time. But instead, you can write it as in terms of the on-policy distribution. So if you define this d pi distribution over state actions as the typical on-policy distribution, then all you need to do is say, well, I'm going to sample some state action pair from this on-policy distribution, look at the reward, and average those. So this on-policy distribution, the math is kind of weird at first glance, but it's a very simple concept. All it says is for any state action, there's some probability that I'm going to encounter that state action when I run my policy. And that probability depends on what time step I'm going to encounter it. And to make things go into just one distribution, we average those probabilities over time steps using gamma discounting. Right, so this is saying the on-policy distribution is saying for some state action, what's the probability I'm going to encounter that state action by running my policy? And so then the value of the policy, the rho pi, is very simply written as, well, first sample a state action for my on-policy distribution, and then look at the reward and average that. And so we can use the importance weighting trick to now write this expectation over on-policy as an expectation over this arbitrary offline data set. And all we need to do is introduce a density ratio into the inner part of the expectation. So in terms of your finite data set, if you have like a bunch of state actions rewards, what this corresponds to is saying, well, I'm going to take an average of rewards I've seen in my data set, but I'm going to weight them by this density ratio. And that's going to be doing the finite analog of the expectation, which should, in the limit of infinite data, give us the value of pi. So now the problem is, how do we actually estimate these weights? So how do we estimate this density ratio? And this problem is pretty hard because, well, one, the numerator, the on-policy distribution, right, we don't have access to the environment, so we can't actually do Monte Carlo rollouts. Even if we could do Monte Carlo rollouts, knowing the density of this distribution is not easy to compute. Right? If you have Monte Carlo rollouts, you only have access to samples, but you don't actually know the density. And similarly with the denominator, we don't know the density of our offline, off-policy data set. We just have access to samples from it. But still, we want to estimate these density ratios. OK, so now we've taken our original problem, off-policy policy evaluation, turned it into density ratio estimation. Still a seemingly hard problem, but it'll at least be more approachable. And the key insight is looking back at the F divergence things we were talking about. So that we said the F divergence can be written as an optimization. So back then, it was a max. This time, I've done a negative, applied a negative to the F divergence so that it becomes a min. Just makes the notation easier. So the F divergence is a min over x of difference of expectations between two distributions. And again, the nice thing about this variational form of the F divergence is that you no longer need to know the explicit densities. You just need to have access to samples from them. OK, so what does this have to do with density ratio estimation? Oops. So we can figure out there's something nice about the optimal x of this objective. So the optimal x we can get a handle on by just taking the gradient. The gradient of the inside should be 0 at the optimal x. And so we can find out that the optimal x should satisfy this. It should satisfy that if you take the derivative of the conjugate function of f applied to x, you'll get back the density ratio. Hopefully you can all see this, because if you take the gradient of this expression with respect to x, OK, you'll get f prime of the conjugate of x, but it'll have a coefficient of the density at state action over here. And then on the other expectation, there's no function, so the derivative is just a constant, 1, but it'll be weighted by a coefficient coming from this expectation, which is the on-policy density. And so you set that to 0, solve for it, and you get this nice result. And so now we have an interesting idea. So, well, let's just optimize this variational form of the F divergence. The x we find as the optimal will then give us an estimate for the corrections using this nice identity. But then we have an issue. So unlike in the previous application where we use the F divergence, we don't actually have access to samples from both of these distributions. We only have access to samples from the first one, from the off-policy distribution. The on-policy distribution, we don't have access to. And so now the question becomes, OK, we're getting closer, but how do we handle this on-policy expectation? OK, so here's the issue. We want to get rid of the on-policy expectation. And now here's another key insight. So this on-policy expectation of x is the same as saying, well, if my rewards are given by x, then what's the average reward of my policy? Right? Remember, we expressed a couple of slides ago the value of a policy in terms of an expectation over the on-policy distribution. And here's the same thing. So we've just replaced the rewards with x. And we're asking, if the rewards were x, what would be the average per-step reward of my policy? And there's another way to measure a value of a policy, or the average value of rewards, and that's with Q values. So instead of a Q value, we'll define this new value, which is sort of the Q value, but with X for rewards. And then we can find that, well, the answer to, well, what is the average reward of my policy is really the same answer as what's the average of my Q values if I were to measure them at the initial state and actions of each episode. Right? Because the Q values at the initial state and action tell me what's my expected future episodic reward. And so the average Q values from the initial states are going to give me my average expected episodic reward. And to turn that into, from episodic to per step, I just need to average by the gamma discounting, which is the same as multiplying by 1 minus gamma. OK, so again, if we take the average of initial new values, or Q values, this new value, you can just expand using the Spellman recurrence, and you'll get the average discounted long-term sum of x by following pi. And that's the same thing as the on-policy expectation of x. So what we're going to do is use that here. So we're going to say, OK, before we had this, right? We had the variational form of the F divergence has this nice property that the optimal x is going to satisfy, is going to give us an expression for the density ratios. And now we're going to write this optimization again, but in terms of new values. So now x in the old objective was just the Bellman residual. And so what we can do is, if we put in new instead, now the first expectation becomes, OK, F conjugate applied to the Bellman residual of new. And then we show that the second expectation just reduces to the average initial new values, right, which are essentially Q values with respect to x. And now, instead of this nice expression for the density ratios in terms of x, we have an expression for the density ratios in terms of the Bellman residual for nu. So all we've done is said, I have some optimization in terms of x. Let me interpret this x as a Bellman residual for some other function. So if I were to write the same objective in terms of this other function, I would get this, which is nice because it's completely off-policy. Right now, I only need to have access to my off-policy distribution, which is the same as before, but the on-policy distribution nicely reduced to only needing access to the initial state distribution. And I will note that I haven't explicitly mentioned convex duality in a while, but this change of variables trick, you can actually interpret it as an application of duality. So if you're familiar with like LP duality, this is essentially doing something like LP duality, where you have some problem in terms of some variable, and then you convert that into a different problem in terms of different variables, but the result should be the same. OK, let me try to provide at least a closer look into all this math. So if we just take f of x equals half x squared, the objective becomes a bit simpler, right? So now we have two expectations still. The first expectation is saying I want to minimize squared Bellman residuals, right? The square is coming from the choice of f. And then the second expectation is not changed much. It's just I'm going to optimize the expected initial new values, which is pretty interesting. So minimizing squared Bellman error, we're familiar with. It comes up a lot in OL. So you can imagine, well, when I minimize this squared Bellman error, what I'm saying is, OK, I have like a bunch of states and actions in some trajectory. And I'm saying, well, for each of these state actions in the trajectory, try to push them close together. Right? Minimize the squared Bellman residual, try to push those values close together. And if we only had this expectation, so ignoring the other expectation, if we were just minimizing squared Bellman residuals, the optimum would be 0. Right? Because again, this Bellman operator doesn't have rewards, right? Because the rewards are x. So the optimal Bellman residual of that would just send everything to 0. But at the same time, we have this other term in the objective, which is inducing some non-trivial solution. So it's saying, the first expectation is saying, I want you to push all these new values close together. But then the second expectation is saying, well, the first state and action you saw in that trajectory, I want you to move it down. Or I guess in this case, make the Q value as big as possible. And what the math on the last slide said is that the optimal Bellman residual now is not 0. It's going to be something positive. And it's going to be exactly the density ratio we care about. So again, this is very nice because it gives us an objective that's completely off policy. Right? We only need access to arbitrary distribution in the first expectation and access to initial states. But there are issues. So again, we come to this issue where we're minimizing squared Bellman error, but we can't easily do that when we only have access to transitions. Right? So we can't, like in that first application I showed you, we can't easily optimize the square without some more convex duality tricks. OK, so now we need to apply these convex duality tricks. So we have this objective. In general, we just have some conjugate function applied to the residual. And we want to take that Bellman operator, that expectation, outside. And so we apply this conjugate trick again, where we say, well, the conjugate of f can be expressed as an optimization over its own conjugate, which is back to the f. So the conjugate becomes f applied to some new variable zeta. And now we've taken the expectation in the Bellman operator outside the convex function. And now, before we had that if you applied the derivative of the conjugate to the Bellman residuals, you'll get the density ratio. Here, if you do the math, you'll figure out that it's actually cleaner, that the optimal zeta, so the optimal dual variable, will be exactly the Bellman residual. So it's pretty nice that we've, with this application of one extra duality, we've gotten rid of both the Bellman operator inside the objective and the Bellman operator in this final optimum step to get back the density ratio. OK, so to summarize, what we've done is we started with the evaluation problem. We've reduced it to a density ratio estimation problem. We used this nice property of the F divergence to get an optimization perspective on the density ratio estimation problem. We had to apply a change of variables trick to turn the variational form of the F divergence to an off-policy form, and we got this nice objective. And then we just applied one more convex duality trick to get rid of the Bellman operator, both in the objective and the solution. So this algorithm is called dual dice, and sometimes the change of variables trick we did is called the dual dice trick. And before we move on to the next application, I'll just ask you to remember this nice expression where the Bellman residual of some optimal new values can get you back the density ratio. OK, so before we get to the last off-pulse CLL application, maybe take another 1 or 2 minute break.
I'm wondering if, in like the off-policy setting, if you previously collected like how exactly useful would this be, considering that like if you previously collected data in form of like whole trajectories, like you can just regress onto like Monte Carlo returns. So,
well, you can only do Monte Carlo regression if the data you have was collected by the policy you want to estimate. Or
right,
you think
the old policy. Right?
Oh, yeah, you can calculate the value of an old policy.
Mm-hmm.
But in this case, in this setting, we have some new policy, like we've maybe gotten it from like some RL optimization. We have a new policy, and we want to know how well would this policy do without actually putting it in the environment. Yeah, and so the mismatch between the distribution we have and the distribution we need to estimate the value is what we're trying to resolve here.
So it seems like could you go back to the previous? So it seems like when you transform the problem, oh no, to the minimax version.
Oh yeah.
Yeah. So there, you're putting the burden now on the optimization, and you're changing the difficulty of doing the estimation of the distribution. Now you're solving this minimax problem. But how hard is solving this problem? Have it in practice or?
In practice, it's. I mean, it's not trivial, but doing basic stochastic gradient descent with like alternating between the variables can work most of the time.
Because you'd have like say one neural network for the Xi and another neural network for the nu. And you're training now both of them.
Yeah, yeah. Yeah, and that's a common theme, right, in these applications where convex duality solves some of your problems, but then it usually introduces an extra optimization. Okay, almost done. One last application, maybe the most interesting one. So don't care about evaluation now. Now we care about policy optimization. So again, like when I mentioned this at the start of the talk, we have some experience data set where we don't know where it came from, but now we want to do OL. So we want to do something like policy gradient. But then the issue is that for policy gradient, you usually need access to the on-policy distribution. And in our case, we only have access to some off-policy distribution. So how do we use the ideas so far on this problem? So let's look at the max return objective. So usually, when you say you want to optimize max return, you write it in terms of Q values. Right? So you say, I want to find pi that maximizes the future discounted value of pi given by the q values. And so now the q values satisfy the Spellman equation, which we're very familiar with. And the Spellman equation is different from the last application, so now it actually includes rewards in it. And then we hinted at this in the previous application, where you can write this expectation over initial q values in this so-called dual form, where instead of q values, you actually write it in terms of the on-policy expectation d pi. And then what we want to optimize is the average of rewards taken from this expectation. So what we'll find is that this dual form, like the last application, will be more approachable. So what we do in order to invoke the tricks we've introduced so far is we add a convex regularizer. So we slightly change the problem and say, well, I want to maximize my average reward, but let's say I also add this regularizer saying my new policy shouldn't be too far from my off-policy data set. But I will note that this regularizer shouldn't be taken as too much of a constraint. So it's really like alpha and f can be anything. So you can set alpha to be like very, very close to 0, and things will be fine. So the f divergence is mostly just as a mathematical tool to enable the future derivations. OK, so we have an f divergence. We'll do what we've done with every other f divergence so far, is look at its variational form. So now we've replaced the f divergence with an optimization over x. So we've got the same, we've still got the expectation over rewards, but now we've got an additional 2 expectations. One of x over the on-policy distribution, and the other of f conjugate of x on the off-policy distribution. So we can combine the 2 on-policy distributions, right? And now we just have 2 expectations again, where the first expectation is on-policy, and it's measuring rewards minus alpha times x. And then the other expectation is off-policy. It's measuring the average value of the conjugate of f applied to x. And what we can realize is that, well, this form is actually very similar to what we had in the evaluation application, where we have 2 expectations. One of them we know how to do, the off-policy. That's easy because we have access to samples from the off-policy data set. But then the other one we don't know how to do because it's an on-policy sample. But we can still use the same trick, right? So we can use this trick of saying, well, the on-policy expectation, I can just write it in terms of some sort of q value. But the q value now is as follows. So the new value is defined like this, where instead of being just with respect to x, so it's minus alpha times x, but then it's plus a Bellman operator. And the Bellman operator here does include the reward term. And so again, we can argue that, well, these new values are going to measure the future average discounted value of pi if rewards were rewards minus alpha times x, so augmented rewards. And so we can write this on-policy average of r minus alpha times x instead of as average over initial new values. So now the on-policy expectation becomes an average over initial new values, and then the off-policy expectation is just replacing x with the Bellman residual of new. And so that's pretty much it, right? So we have a completely off-policy form of the on-policy max return objective. And then computing the gradient of this like when you optimize pi, when you do that max pi outside of the min x, all you need to know is, well, samples from my off-policy distribution and samples to the initial state distribution. And then if you want, you can apply an extra dual embedding trick again, right? Because again, we have a Bellman operator inside a convex function, and you can do that dual embedding trick. But I won't get into that because that's, hopefully you know what'll happen. OK, so that's the off-policy objective. The really cool property of this happens when you consider how will I actually optimize pi. So when I optimize pi, I'm going to compute the gradients of this objective. And what we'll find is that the gradients actually turn out to be the on-policy gradients. So I'll show you how that is. So we're taking the gradients of this objective. So we have some objective given by j pi of nu, where we have an expectation over initial states, and then this off-policy expectation of some conjugate of some expression, the Bellman residual. And so if we say, let's say we like optimize the inner min, so we found some nu star, some optimal nu star for a pi. And now we want to take the gradient of j. So the important fact is that this expression I asked you to remember, where if you've optimized nu star, then you have this nice expression for the density ratios. If you take the Bellman residual of nu star, apply the conjugate of f star to it, you'll get back the density ratios. And so what this means is when you take the gradient of this term, the off-policy term, you're going to have to use the chain rule. And the first step of that chain rule will take f conjugate prime of the Bellman residual. And that f conjugate prime is this density ratio here. And then there's some rest of the chain rule. But really, this is pretty much the main benefit here. So we get back the density ratio. And now we have this nice trick again, where the denominator of the density ratio cancels out with the expectation. And then you just get back the numerator of the density ratio, which is exactly the on-policy distribution. And then the rest is pretty standard. You can combine these two expectations into one, and you'll figure out that the gradient with respect to pi is the on-policy expectation of new values times grad log pi. Right? And this is pretty cool, because now we are exactly doing on-policy policy gradient. This is exactly on-policy policy gradient, but instead of q values, we have new values. And you can show that the new values are almost q values. They're like reward, average future reward plus some regularizer. OK, so that's the main cool property. We've taken our on-policy max return objective, used convex duality to convert it into an off-policy objective, but the gradients are still on-policy policy gradients. So if we take a closer look at what the objective looks like with this simple square function, we get the following. All right, so now this off-policy expectation just becomes a square of Bellman residuals, which is pretty intriguing. It's similar to actor critic, where you also minimize the square of Bellman residuals to learn some q-value function. But in actor critic, you then use that q-value function to optimize your policy to maximize q-value functions. But in our case, we use the objective to train the critic, the q-value function. The same objective is used to train the actor, the policy. So it's similar to actor critic, but not quite. But there is this interesting connection. OK, so to summarize this last application, we took the dual form of the max return objective in terms of state action occupancies or densities. And then we added an F divergence regularizer in order to enable all these subsequent derivations. Right? We have an F divergence, write it in a variational form, apply the dual dice trick, and that's all it takes to get the off-policy formulation of the max return objective. And then we show that if you actually optimize the critics, so-called, or the Q-values, so-called, then the gradients which you compute as an expectation over off-policy data are actually exactly equal to the on-policy gradient. And that's it. So that's the end of the talk. So we've gone over convex conjugates. I've given you the bare minimum you need for like 99% of the cases, right? It's pretty easy. The 2 or 3 things you need to know are pretty easy to know, and the rest is just formalisms. And we've seen this in a variety of applications, right? The square-Bellman residual, regularizing a policy, off-policy policy estimation, and off-policy RL. Although in each of these cases, it's important to note, right, there's always a trade-off. And the common trade-off is, well, now you can do maybe off-policy stuff, or you don't need explicit knowledge of distributions, but a lot of times you have to do an extra optimization. And that trade-off, it depends on the context, whether it's worth it. So I'll list a couple papers, but unfortunately, a lot of these papers will be out soon. So a lot of it is current research I'm working on. And that's the conclusion. So we have a good amount of time for questions, if any.
What are example environments or applications that you have tried with dual dice or any of these algorithms, off-policy RL algorithms so far?
So a lot of these, I think almost all of them have been at least tested on like simulated robot environments, like the Majoko, Cheetah, and like Walker, and all those. Yeah, I know some of these are also like regularizing a policy to behavioral data shows up a lot. I think some of these techniques also have been tried in practical applications as well.
Is there code online for that, or?
Yeah, I know at least one of my projects in this space has been open sourced recently.
Okay.
Yeah. I think it's called BRAC, BRAC. It's in the Google Research GitHub folder.
Any other questions? All right. Yeah.
All right.
Thanks, Ophir.
Thanks for coming.
Cool.
Went pretty fast.
That was really cool. Yeah, very interesting framework.
Mm-hmm.
I think, yeah, off-policy is the next important thing to get.
Yeah,
like,
people are getting
reuse
excited
the data,
about it.
not need to recollect the data each time.
Yeah. Wait a second.
I actually did have a question. You utilize dual embedding a lot in that deck. Did you ever use strong duality to transpose your maximum? It looks like in the minimizing square Bellman residuals, you set like a concave expression on the inside.
Yeah, in that application, I haven't thought about it much. But what's interesting is you can, the off-policy RL stuff, you can interpret that as an application of strong duality.
Okay.
So the change of variables is really a strong duality
Yeah, because LPDO
application.
And when you implement these like maps, do you do an alternating minimization over the policy and new?
Yeah, just simple. Take a gradient step in one, gradient step in the other, and
Got it.
repeat.
And is that stable?
It's stable enough.
Yeah, maybe it's RL.
Theoretically, you're not. It shouldn't work in general, but there's nothing really better you can do, and it works fine.
Oh, so theoretically, it's there's no actual equilibrium point.
Right. Yeah. Theoretically, there aren't many useful results for it. What theory says is you should optimize the inner one to completion before taking any gradient steps in the other. But that's not really feasible.
Yeah.
So you're just taking one gradient step of either and alternating.
Yeah. I mean, same thing happens in a lot of settings, like with GANs. They also just do alternating gradient descent when you shouldn't really do that if you want it to be theoretically optimal.
Yeah, I see. And how do you parameterize new?
Just a neural network.
Okay, like a MLP from states and action.
Cool. Yeah, I was trying to ask how does it perform, like if you have baselines?
The things we've tried perform pretty well. Like if you, this off-policy policy about estimation thing will be at NOIPS this year, and we compare it to like a bunch of existing things like importance weighting. There's like a bunch of other things that like estimating the Q values and taking an average of that, and it performs better than all these, despite all the downsides of extra optimization and potential instability.
So are you like building this formalism based on some existing algorithms, and what are they?
Definitely a lot of the stuff here is built on a lot of previous work, like
yeah, I guess. Then what about in the actual experiments? Like how are the experiments conducted?
The experiments are more similar to previous work, where like the new value is really just a Q value, right? So it's just like you take your Q value MLP neural network and now call it a new value and just change the objective function that it trains for. Does that answer any lingering
that was a
questions?
clear question anyways. So you expect the new value to be close to Q values?
Yeah, mathematically it's the optimal new value is the Q values plus Q values for like an augmented reward.
Mm-hmm.
So the augmented reward would be like your original reward plus some coefficient times some function of the density ratios.
Okay. Yeah. Thanks.
Sorry, I'm just checking out the paper. Any idea why P equals 1.5 performs?
Oh.
I'm just curious about your guess.
I don't have any good insights, but I guess it just has to do with like the optimization landscape. That when you, in practice, when you have to do like alternating gradient descent, then the shape of your loss function matters, and one of the exponents will be optimal. For some reason, it was 1.5 for us.
Interesting.
What is P?
You guys use one. So like instead of 1/2 x squared.
Yeah. Okay.
They used, was it 3/2 absolute value of x to the 1.5.
Okay. Is that also solvable?
Also what?
So the convex conjugate of
Oh, yeah.
equal to itself also?
Not to itself,
Okay.
to some other convex function.
Cool. Thank you.
Thank you so much.
Yeah.
Cool. Then let's head over to SDH.
Okay. Just need to be in here.
Yeah, probably a good idea to put it back.
Okay. Cool. Hopefully that's fine.
Yeah, that was really interesting. I'm very curious to look at, like, to see if we would have some applications where we definitely have a lot of applications where we want to use off-ball CRL. So you said at Google they used that dual dice, or?
Not dual dice specifically. There's a lot of applications where regularizing to behavior policy is used.
Okay. So like stay close to the behavior policy.
Yeah.
Okay.
Even though you don't know what the policy is.
But the off-policy evaluation and the off-policy RL, has that been used so far, or?
The specific algorithms I discussed, no.
Okay.
Yeah, and that's mostly just recency.
Yeah, because it's
Dual
very,
dice.
I'd be very curious to see. Yeah, I'm wondering like what are the existing choices that people had to do off-policy evaluation?
Mm.
What did people do before? Did they just ignore the problem? Or?
No, well, sometimes. I think what's had the most success is weighted.
Okay. Wasn't that unstable?